As h approaches 0 of f of x plus h minus f of x all over h. All right. So you develop a semblance of familiarity here, although it's not ideal. You start to get a handle on what's expected. The f of x plus h is what you would get if, again, you replace your x with an x plus h. So cosine 5x plus 5h that's going to be our f of x plus h. We're going to subtract from that cosine 5x and put that all over h. The expansion is where all the magic's going to happen. All right, so we have to apply our cosine rule, or double angle, some identity for cosine. So that's going to become cosine 5x, cosine 5h. The plus becomes a minus by rule. Sine 5x, sine 5h. Minus the cosine 5x that's already there, all over the h that's already there, with the limit as h approaches 0 preceding the whole thing. All right, so then we want to reorganize. The reorganization part of it isn't too bad because it's consistent with the other 3 times we did a problem similar to this. Anything that's got a 5x in it, or I'm sorry, cosine of 5x is going to go together in its own fraction. So cosine 5x. Oh, I just realized as I was about to rewrite my little typo there. My handwriting O, I mean. Cosine 5x, 5h, what that should have said. So cosine 5x, cosine 5h, minus cosine 5x, all over h would be one fraction. Then minus sine 5x, sine 5h, all over h would be the other fraction. All right. Now we're applying the limit to the whole thing, but one thing that we've kind of learned to streamline along the way is putting the limit in front of each piece rather than the limit in front of the whole thing, just to then, in the next step, put it in front of each piece. So I'm going to write this as limit as h approaches 0, then limit as h approaches 0. So then I'm going to pull out a quote-unquote GCF, but that GCF in the first fraction would be a cosine 5x. In the second one, it would just be a sine of 5x, because those are factors that don't involve an h. All right. Those two limit expressions are each pretty close to being rules, except each one of them is missing a little something. All right, that little something is not too substantial. It's the little something. All right. We need the argument of the cosine function to be the same as the denominator. So if this is a 5h in this case, this needs to be a 5h. Same deal here. All right, so what we do is we multiply top and bottom of each of these fractions by 5. But what we do with them from top to bottom is different. So that 5 in the denominator would get grouped with the h. That 5 with the numerator would get factored out of the whole thing. All right. So the 5 in the bottom of the fraction gets grouped with the h. The 5 on the top of the fraction gets taken out of the whole thing. All right. So you could do that all in one shot, or you could just, show it in the next step. The same would be true for the other limit. The 5 on the bottom would get grouped with the h. The 5 on the top would get factored out of the whole thing. So that would give us a negative 5 sine 5x limit as h approaches 0 of sine 5h over 5h. All right, each of which constitutes a rule. First one goes to 0, making all of this irrelevant. The second one goes to 1, which tells us that this entire expression is going to amount to just a negative 5 sine 5x. And so that would be my derivative. Notation-wise, f of x, so f prime of x. All right. So now we want to, again, generalize that. We want to think about, okay, how can we get from question to answer without doing all that other stuff? All right. And it goes back to what we were talking about last time. We had sine of x has a derivative of cosine of x. Sine of 2x had a derivative of 2 cosine 2x. All right, so what happened was we had a 2x that made up the argument of the trig function. So not only was that maintained within the derivative function, the trig part of the derivative function, but it also manifested itself as part of the coefficient. All right, so here we're saying 5 cosine, oh, actually it was just cosine 5x. 5x corresponds to negative 5 sine 5x. So same deal, that 5x carries over. The argument of the cosine function becomes the argument of the corresponding sine function. And we still have that leading coefficient relationship. All right. Now, if you just look at what this relationship is between the 2x and the 2, that 2 is really just the slope of the line y equals 2x. Or you could just look at it and say, well, it's the coefficient of x, but that's the same thing as the slope. All right, so this is really the derivative of 2x. This piece would really just be the derivative, little derivative notation, of the 5x. So it's really just telling us to plug in if you know that the derivative of sine is cosine, plug the 2x in for x, but then multiply the function by the derivative, all right, of whatever that inner expression is. So we can test that out. You know, we can test it out with a bunch of different possibilities, but we'll keep it simple at least to start. Let's say we have f of x is equal to the sine, I don't know. Well, there's one right there that says 3x. I don't know that I necessarily, you know what, I'll start with that one. Sine of 3x. All right. I think the derivative of that, well, sine has a derivative of cosine. I think it's going to be cosine of 3x, but I would also need to multiply it by the derivative of the inner expression, that 3x. So I'm going to pop a 3 in front. Now the graph's messy, but I only really need to see what I think the derivative is. This is what I think the derivative is. I'll write it down. Let's see what Desmos thinks the derivative is. F prime of x, same graph. All right. So our trend seems to work, but you could also kind of jazz it up and say, all right, well, what if it gets a little spicier? Like maybe, and you know, this is going a little off the grid here, but let's say it's sine of x squared. All right. Well, I think the derivative of that should be equal to cosine x squared, but then we should also be multiplying by the derivative of whatever's inside the sine function. And the derivative of x squared would be what? 2x, yeah. All right, so I think the derivative is 2x cosine x squared. They think it's the same thing. They just didn't tell me that. They showed me the graph of it, but it's the same. All right, so it looks like we're onto something here. We got a nice rule for trig functions. The idea that all you'd have to do is know the derivative rule for sine and cosine. And again, I'll just make sure it's on the notes here. The derivative of sine of x, close bracket, is equal to cosine of x. All right, and all this notation is really just saying is the derivative of this function. All right, we'll get into more of the bits and pieces about why the different forms of notation look the way they do as we go forward. But for now, it's just another form of notation for derivatives. It's a very shorthand way of writing it. The derivative of sine x is equal to cosine of x. Plus, the derivative of cosine of x is equal to negative sine of x. So if I know that framework, what if I don't want to answer? If I know the framework is negative sine of x, then all I'd have to do is pop in the new argument, 7x, and multiply by the derivative of that 7x. The derivative of 7x is what? 7. And now we have it. I had every intention of answering the phone after I finished that problem. But they stopped, calling, so how am I supposed to control that? So if you're ever in doubt, you Desmos it up and have a look. Cosine oh, well that got really ugly really quick. Cosine of 7x. I think that derivative is negative 7 equals negative 7 sine 7x. It's a messy graph, but they are the same. All right. So then the remaining problems here, just kind of break it up into different, sums and differences of different functions. All right, a trig function, a power function, and then a constant function. So cosine of 2x is going to follow what we just did here. So that should be, again, following the structure of negative sine x, just with a 2x inside, and multiplied by the derivative of 2x, is going to be negative 2 sine 2x. The negative x cubed, remember that's an assumed negative 1x cubed. So the derivative of that would be negative 3x squared by the power rule that we discovered, where you just multiply the power by the coefficient and then take away 1 from the power. And then a constant has a derivative of 0, because remember, that's more philosophical, but you could also do it mechanically. But if you just think about it, if something is constant, it's not changing. If something is not changing, then its rate of change would be equal to 0. Right? And therefore, its derivative would be equal to 0. Right? Cosine 4x. Then we have a little trig function going on here, and then we got another power relation. Oops, different color. So cosine 4x, again, it would become, if it were just a cosine of x, it would become negative sine of x. So we know it's going to be negative. It's going to have a sine of 4x, but we're going to multiply by the derivative of what's inside the function. Derivative of 4x is equal to 4. All right. Now, the second one is probably the crunchiest one out of all of them, because that has a coefficient on the sine function. But we could actually just leave a coefficient alone, at least temporarily, because if you really think about it, the sine function under normal circumstances is just going to be cosine, but when we correct for the fact that it's got an inner function that's not just an x, we multiply the leading coefficient by whatever the derivative is of that inner function. All right. In most cases, the leading coefficient has been equal to 1, so it hasn't really affected much of an impact. All right, but here, I'd look at this and say, all right, I got a negative 3. I just leave that alone for a sec. I'm going to just focus on the sine of 2x. Sine of 2x has a derivative that's equal to cosine of 2x. I'm going to take the derivative of that inner function and multiply it by the coefficient that's already there. Just like we would with a power rule situation. If there's a coefficient already there, you just multiply by the coefficient that's already there. We'll see that in a second, actually. All right, the derivative of 2x is just 2, so I'm going to multiply by a 2. All right, and then the last piece is just 8x cubed. That's just power times coefficient and reduce the power by 1. And then simplify if you need to. And by need to, I mean the directions tell you explicitly to simplify. But if they don't, you don't have to. You'll get to points in time where you'll decide that it's appropriate to simplify. You won't need me to tell you that. Okay. Now, I'm just going to take you through one more problem, because these involve the other types of functions.
That's supposed to be 8x to the third, right?
It sure is. Thank you. Very good. All right. So the secant, tangent, cotangent, all that good stuff. Got to go back to scratch. Got to investigate and identify some rules here. But it's going to boil down the same way, where if we can just figure out what the derivatives are for these types of functions, then if these functions are modified in any way, like instead of secant of x, let's say it's secant of 2x or secant of 5x, we're going to be able to rely on the same sort of relationship that we just discovered for sine and cosine. Because this you probably should remember from algebra and pre-calc and all that good stuff, is that all the trig functions are rooted in sines and cosines. In fact, every trig function could be written in terms of sines and cosines. So if you know everything there is to know about sines and cosines, you could figure out on the fly everything that there can be known about all the other trig functions that might exist. All right. So back to scratch. Limit as h approaches 0. So f of x plus h is going to be secant x plus h. All right, we didn't have a sum and difference rule for this. If you go back to a couple pages ago, there was one for sine, there's one for cosine, but there wasn't one for every other function. They exist, but I didn't write them there. And the thought process there was, well, let's not write all those and worry about different variations of those rules when we can just write secant as 1 over cosine. You got to do a little bit more algebra in the early goings, but it'll help once you get that taken care of. And in fact, this will be easier computationally than some of the other problems that we've done. It just won't seem like it right away. All right. So I have 1 over cosine x plus h times, or minus 1 over cosine x. If I want to add or subtract two fractions, we know that we need to get a common denominator and put them together. All right, I have a fraction over another fraction, so that makes it even spicier, but that's okay. I'm going to multiply top and bottom here by cosine of x. And I'm going to multiply top and bottom here by cosine x plus h. You could try to expand with the cosine rule, but I mean, ultimately we're going to have to add the fractions together anyway, or in this case subtract. If you expand using cosine, cosine a plus b, I mean, it's going to make things messier, and when you want to add two fractions by getting a common denominator, it's better to do it with simpler expressions. All right. So limit as h approaches 0 of cosine x minus cosine x plus h over our common denominator, cosine x plus h, all over an h, but that over h part can be written as h over 1. You could actually save yourself a step there, because that keep change flip action, that's going to put the h in the bottom of the numerator fraction. All right, so you'd be looking at limit as h approaches 0 of really just all this stuff again, just with an h on the bottom after the keep change flip. All right. So there was that extra step of putting the two fractions together, make it a little bit more concise. But now that we have that, we want to expand this out using our rule, and that's where things are going to start taking off. It's going to get a whole lot nicer in a sec. All right. It just gets a little uglier before it gets a little nicer. So cosine of x minus, so then we need our sum rule for cosine. Cosine x, cosine h, minus, and remember it's the reverse sign for cosine. It's fun to say. Sine x, sine h. All over that lovely looking denominator. which comparatively speaking isn't as bad as some that we've seen. Let me get a different fraction here. Bring this down. And again, it doesn't seem like we're going anywhere good in a hurry, but once we distribute and split up our fractions, everything's going to come out beautifully. All right, we have a negative that could be distributed through, so we'll do that. Limit as h approaches 0, cosine x minus cosine x cosine h plus sine x sine h over h cosine x cosine x plus h. All right, it's still not the easiest thing in the world to see in terms of how it's all going to work out, but we do have a common cosine x, and that's something we can latch onto. And that's been a common thread. You have the common factor that you can pull out, so we can actually factor that out, but we need to split the fraction first. So I'm going to write it as cosine x minus cosine h, cosine x cosine h over the denominator plus sine x sine h over the denominator we have a common factor that could be canceled out, or factored out and canceled out. All right, so that's the cosine x, top and bottom actually. So I don't even have to pull it out of the whole limit. I could just pull it out of the fraction and write it as limit h approaches 0, cosine x 1 minus cosine h over h cosine x plus h. And for the second piece, there isn't a common factor that could be pulled out, but there is something that we can do with it. And in fact, there's something further that we can do with both of them. It's just I'm going to save that for the next step. So I'm just going to rewrite this one. So the cosine x's cancel. And so now what we're going to do is apply a rule that I don't know that too many people actually remember is a thing that they can do with limits. All right, you can split a limit up based off of not just sums and differences, but you can split it up based off of products and quotients. So I'll show you what that looks like in a sec. So here what I'm going to do is I'm going to split up this fraction because I see that I have a 1 minus cosine h over h, which is good. I'd like to have that. That's a rule. So I'm going to pull that out and make that a factor, with the other factor being whatever's left, 1 over cosine x plus h. And I would do the same thing with the second fraction. I got a sine of h over h. I can pull that out and make it its own fraction. I still have a plus sign separating the two, but sine h over h, which is a rule. If we're applying a limit as h approaches 0 to it, it's a rule. And then everything else would make up the other fraction, sine x over cosine x plus h. All right. The idea of splitting up fractions, that's not what I was talking about when I was saying that there are rules that people forget. The rule that I'm talking about is the rule of limits that tell you that you can actually apply the limit to each piece of this expression separately. All right, one piece at a time. And that's going to be the key to taking this the rest of the way. So I'd say limit as h approaches 0 of each part. So the limit as h approaches 0 of this, limit as h approaches 0 of this, multiplied, plus the limit as h approaches 0 of the sine h over h, times the limit as h approaches 0 of this. All right. So the limit as h approaches 0 of 1 minus cosine h over h, that's equal to 0, which makes the first half of this expression irrelevant, because it's all going to cancel away. This piece is equal to 1, so that becomes irrelevant. So the only thing that's actually relevant in this whole remaining expression, or out of this whole expression, is this last limit here. So I apply the limit. I substitute in 0 for h. When I do that, I get cosine of x plus 0, which is cosine of x. Cosine of x times cosine of x is cosine squared x. On the top, we have a sine of x, and that would be our derivative, right? Or at least one variation of it. The people who are in charge of writing textbooks and stuff like that don't like this form of the derivative. I think it's beautiful. But what they like to do instead is write this as sine of x over cosine of x multiplied by 1 over cosine of x. And I'll tell you why in a second. I think it's the dumbest thing in the world, but it is. It became like a rule, like a universal rule. They split up the fraction, they make it into two separate factors, and they write this as secant of x times tangent of x. All right. So this is actually the preferred rule for the derivative of secant. Secant of x times tangent of x. But the reason why has nothing to do with convenience or anything like that, you know, which one is more useful in a mathematical context. It has everything to do with the fact that secant x tan x was easier to type in previous years when they didn't have word processors and they actually had to type textbooks using typewriters. They couldn't make fractions very easily. So anytime they could make a rule that was not in a fraction form, they wrote it that way. Same thing with exponents. They could avoid writing it as a fraction and put it with a negative exponent. They prefer to do that because it just made things more convenient.
What happened to like the other factor, like the 1 over cosine x plus 8?
Irrelevant, because this one is equal to 0 and 0 times that is 0. All right, so obviously this is the craziest one ever, but if you look at this and you say, all right, I have a rule now. F of x, if it's equal to secant of x, it has a derivative f prime of x is equal to secant of x times tangent of x. Then you start thinking, all right, well, what if I have f of x is equal to secant of 5x? Well, you just think about what we did here. Its derivative is going to swap out each of these arguments for our new argument, secant 5x, tangent 5x. The only thing we'd have to remember to do is multiply by the derivative of that inner function, which would be a 5x. Derivative of that would be equal to 5. So by discovering the basic version of the rule, which is, simple in terms of its final answer, but not simple at all in terms of how we got there. But making that discovery the one time allows us to rely on that for more complicated situations. All right. So now all we have to do is discover 3 more trig rules, and then we'll be good. All right. So you're actually qualified now to be able to handle number 9, but definitely not numbers 7 and 8. All right. This one, I always forget. This one ends at 42, right? So we're pretty much done. So tomorrow we'll do number 7 together, but then you'll have time to work on 8 and 9 with the idea that, hey, maybe you can discover those rules, and then we'll be good to go. All right? There will be an element of memorization when it comes to being able to take derivatives, but understanding the structure is going to be the most important.